Okay. Question is simply to graph this quadratic function. Now, form is y equals ax squared plus bx plus c. A equals 1 because what's in front of x squared? Well, there's nothing in front of x squared. That means you just got 1x squared, right? And b equals 7. And c equals -3. So x equals 0 if IFF means if and only if x equals -b plus or minus square root of b squared minus 4ac, all that divided by 2a. And that's the quadratic formula that you simply have to know. Okay, not that hard to use it a few times, you'll remember it. And then b is 7, so negative b would be -7 plus or minus the square root of b squared would be 7 squared minus 4ac would be -4 times 1 times -3. And then you divide all that by 2a, which is 2 times 1. Then you simplify that. Well, everybody can do the arithmetic, except maybe me. I'm probably going to screw it up. But 7 squared is 49. 4 times 3 is 12. And 4 times 1 times 3 is 12. And you got a negative in front of it and a negative on the 3. So that means it's going to be 12. And 7 squared, then 49, add 12, you get 61. I think we got that on one of the examples last time. Okay, so you get -7 plus or minus the square root of 61 over 2. Now at that stage, you're welcome to use a calculator to do the square root of 61. Okay, it's about 7.8, give or take a little. So we get -7 plus or minus 7.8 divided by 2. Okay, well, let's stop there because I'm running out of space and come up, start a new column. Okay, so again, x equals 0 if and only if x is approximately equal to -7 plus or minus 7.8 over 2. So x equals -7 plus 7.8 over 2 equals 0.4, or x equals -7 minus 7.8 over 2 equals -7.4. So now we can begin to sketch a graph. We found the zeros. We found where y equals 0. Okay, y equals 0 if x is 0.4. So I'm just going to sketch a vertical line here and label it x equals 0.4. That's a line pretty close to the y-axis. And then over here, well to the left, where I think x equals negative 7.8 might be. I'm not sure my scale is totally consistent. It is somewhat reasonable. Then I'm going to mark a point on the x-axis where x equals 0.4 and a point on the x-axis where x equals negative 7.8. I know my graph is going to go through those 2 points. Okay, also the y-intercept is at y equals f of 0, which is negative 3. Why did I use x equals 0? Because the y-axis is where x equals 0. To get the y-intercept, as I've been preaching for months, okay, and I think you all know, we plug in 0. And it's real easy to plug in 0 here. Everything that has an x on it's going to be 0. And the only thing got left is that negative 3. That means I can put the point 0, negative 3 on the graph. So I'm going to put that about here. I'm going to draw a horizontal line a little bit below the x-axis for y equals negative 3. And I'm going to put the point there. And I'll go ahead and label these points now. I kind of see where the graph is going to be. The point I've got on the x-axis at negative 7.8 is, of course, negative 7.80. And the point I have at x equals 0.4 is 0.4, 0. And the y-intercept is 0, negative 3. At this point, I can draw a nice parabola, goes through all 3 points, okay? But I don't want to do that yet. I want the axis of symmetry. Remember that a parabola is symmetric about a vertical axis. One side is the reflection of the other. The y-intercept in this case is going to be halfway between, the axis of symmetry will be halfway between the x equals 0.4 line and the x equals negative 7.4 line. And I mislabeled that. We figured that 0 would be at negative 7.4. I used 7.8 that I had before. Okay. Okay, does that make halfway decent sense? Well, what's halfway between 0.4 and negative 7.4? Well, we add 0.4 to 7.4, negative 7.4, and divide by 2, and we get negative 3.5. Why should it be x equals negative 3.5? Well, because that's what we get that's halfway between our known zeros, assuming we calculated the zeros correctly. So one reason is it's because 0.4 plus negative 7.4 divided by 2 is negative 3.5. So negative 3.5 is halfway between your zeros. And because the axis of symmetry is at x equals negative b divided by 2a. Right here in the quadratic formula, you see x equals negative b over 2a. Since you have negative b plus or minus this square root here, negative b over 2a is going to be halfway between the two numbers you get from this formula. Because, one plus the square roots to the right, minus the square roots to the left, right in between is negative b. And you got that 2a in the denominator. You can figure that out. I'm not going to write out the rest of the calculation. I said, and because the axis of symmetry is at x equals negative b over 2a, which is negative 7 over 2 times 1, which is negative 3.5. You can do that in your head very easily, okay? So that confirms that this is the axis of symmetry, two ways, and it's good to check yourself. If you've got two zeros, you can average them and get the axis of symmetry and then check that against the equation x equals negative b over 2a, which you can pull right out of the quadratic formula. Okay, well, now we have the axis of symmetry. The vertex has to be on the axis of symmetry so that our function is going to come down kind of like this. Going to kind of level off, and that's going to come back up. It's going to be nice and symmetric with respect to this axis of symmetry. I did draw that exactly right. I'm going to draw a more solid line here in a minute when I figure out exactly what the coordinate of the vertex is. So the vertex you want to find y for x equals negative 3.5 because the vertex lies on the line x equals negative 3.5. Okay? Well, f negative 3.5 is negative 3.5 squared plus 7 times negative 3.5 minus 3. Negative 3.5 squared is, I think, 12.25. 7 times negative 3.5 is 21, and negative 21, and negative 3.5 is negative 24.5, and then minus 3. You do all that, and you get 12.25 minus 27.5, which is negative 15.25, I think. Okay. So we get y equals negative 15.25. I'll put a little question mark there. I did that in my head. And, My head doesn't always get it right. Fair enough. So we need a line for y equals negative 15.25. Let's put that down about here. Now, if negative 3 is here, negative 15.25 should probably be a little lower than that. But when I sketch this white curve here, I didn't quite nail it. And one reason for that is this x equals 0.4 line should actually be a little bit closer to the y-axis. In any case, you come down like so and like so, come down to a vertex here, and then curve back around. And that's not a great parabola. Should have been steeper over here. But you get the idea. So we label the vertex. Negative 3.5, negative 15.25. That up a little bit. And if I've done the calculations right, that's the whole procedure. You got to practice that a little bit. But it's just step by step. Steps are always the same. Except sometimes when you do the square root thing here, you get a negative under the square root, which means you don't have x-intercepts. All that means is that graph's either above the x-axis, opening upward, or it's below, opening downward. Okay? You're still going to be able to get the axis of symmetry whether you have two zeros or not. All right? So you want to get that down. I guarantee you, when you have your next test, is going to be on it. And actually, I might even put it on this test as an optional problem. If you understand it, then there's no reason not to do it. It would be a no-risk problem. One of those, if you get it, if it helps your grade, I'll count it. If you ignore it or if you screw it up, I'll get you next time. Okay? Fair enough? All right. Now we want to go on and talk about polynomials and their graphs. Give me 1 second. What's a polynomial? I'm going to define it as it's a product of linear and irreducible quadratic factors. Now, what in the world does that mean? Well, I'll do some examples. A product of linear factors could be 2x minus 7 times x plus 3 times 47x minus 98 times 2x plus 5. Okay, these are all linear. If I did y equals 2x minus 7 by itself, it would give me a straight line graph with a slope of 2 and a y-intercept of -4. Okay, If I did y equals x plus 3, give me a graph with an y-intercept of 0, 3, and a slope of 1, and so forth. Each of these could by itself be a linear function with a straight line graph. When you multiply them all together, well, if you multiply two of them together, you get a quadratic graph, which is just we just saw. Okay? If you multiply three of them together, you get a cubic graph, which means that the shape of the graph, if you zoom way back, is going to be like an x cubed power function. Okay? And you got to know what those power functions look like and how they behave. And I'm not sure everybody say, at least, you know, I saw some fairly good work on power functions in the homework. So we're going to talk more about that. Okay, so that's a product of linear factors. So we could call that P of X. Now, can you give me a number for which P of X equals 0? Can you hold up fingers or something? Is there a number you could put in for X that would make this whole thing 0? No, if you put in 0, that's important because it's going to give you the y-intercept. You let X equal 0, you're going to get just -7 times 3 times -98 times 5, right? You can multiply it out in your head real easily. Okay? Not that easy, but that'd be -21. That'd be -105 times -98, which is around 10,000 something. Okay? I want to take a couple of minutes. I probably get that. Just multiply 105 by 100, you get 10,500, and then subtract 210, and you get 10,290. So, and it would be positive. And maybe what I said was right, maybe not. Okay, the point is P of X equals 0. Well, if X equals -3, what do you get for this factor? -3 times 2 is -6 minus 7, that's -13, right? -3 plus 3 is 0. Well, you can stop right there because these things are all multiplied and you got a 0 in there. Multiplying a bunch of things and at least one of them is 0. The whole thing is 0 because when you multiply by 0, you get 0. Okay? Another possibility is 3.5, which we just coincidentally saw on that quadratic function. It has nothing to do with this. But if X equals 3.5, 2X is 7, you get 7 minus 7, right? X equals -2.5, 2X is -5. Add that to 5, you get 0. Any number that makes one of these 0 is going to make the whole thing 0. Well, we can do kind of like we did. We could say, okay, 2x minus 7 could equal 0, or x plus 3 could equal 0, or 47 minus x minus 98 equals 0, or just got room here, 2x plus 5 equals 0, right? And each of these is a very easy equation to solve. Linear equations are always easy to solve. So this gives us x equals 3.5. This gives us x equals -3. This gives us x equals 98 over 47, which is 2 and 447. It's just a little more than 2. It's approximately 2.1. a little less than 2.08 or something like that. Or x equals negative 2.5. Make sense? Right now, we've got enough information to start graphing this thing. At x equals negative 3, at x equals negative 2.5. At x equals 3.5. And at x approximately equals 2.1, we have x-intercepts, points on the x-axis. We also have a y-intercept. If I did my arithmetic correctly, this should be at y equals 10,290. And I think that might be right. I'm giving myself a 50-50 chance of having done that right. Okay. So your scales aren't equal. You know, here's the total span of about between 6 and 7. And right here is 10,290 in the vertical direction. But that's what polynomials are. They get out of hand. Their y values tend to get out of hand. Doesn't mean you can't deal with them. So we have a point here on the y-axis at y equals 10,290. What's on the x-axis at x equals negative 3, negative 2.5, about 2.1, and 3.5. So now we got to draw a curve that goes through all these points. Okay? We got to do the long run behavior. Now, the first section in the chapter asks about the long run behavior of some power functions. Okay? Long run. Okay, if I multiply all of this out, use a distributive law to multiply the whole blank thing. At some point, I'm going to be multiplying 2x by x and multiplying that by 47x and multiplying that by 2x. Okay? That should give me 188x to the fourth. Okay? We get 188x to the fourth plus lower power terms. Okay? We get some x cubes, and we get some x squareds, we get some x's, and we get some numbers. And of course, the numbers we get on the end would multiply out to 10,280. So that'd be the last number. So I could even put that here, 10,200, I said 280, but it's 290. Concentrate on the highest power term. 188x to the fourth is pretty much what we're looking at if we zoom way back on this graph. Okay. So what's a graph of y equals 188x to the fourth look like? Looks like a fourth power graph. And of course, you got to know what the powers look like. That's why you did section 3.1. It's going to look like this. Kind of like a parabola, but quite a bit flatter near the vertex. Okay, so section 3.1 familiarizes you with this. This graph just keeps getting steeper and steeper. So it approaches in plus infinity as x approaches negative infinity. In other words, as we keep going to the left, the thing keeps going up faster and faster. And it's going toward plus infinity as we go to the left. Okay. And as we go to the right, it approaches plus infinity as x approaches plus infinity. So that means the graph has got to go up steeply here. It has to go up steeply here. Because all this lives inside of this graph. This is where we zoom back and, maybe we zoom back, don't have to zoom that far back to where maybe x equals negative 10 here and x equals 10 here. Okay. And if x equals 10, x to the fourth is 10,000. Okay. And your y values would be close to 2 million. Okay, so that's what we're looking at this graph. So maybe x equals negative 10, x equals 10, and y equals 2 million. You don't really need those numbers, but you want to understand that these numbers are really huge if we just go out as far as negative 10. On the scale of this graph, if negative 3 is here, negative 10 is about here, and it's going all the way up to 2 million. So you know it's going up that way. Okay? And similarly over here. Okay, so to draw your graph, you got to come down like this, real steep, and you got to go through this point, but then you got to kind of quick turn around so you can get back up to this point. And let's see, this point, you probably don't peak right at that point, but maybe you peak a little before it. Then you go down here through here, and then here, and then you go way up steep. Okay? The graph has to be a smooth curve. Polynomials always have graphs that are smooth curves. Okay? So that's just a demonstration of what your book tells you, what your open math is going to tell you, what any text will tell you. Okay? You find the zeros, you find the y-intercept, and you look at the long run behavior. You put it all together, you got your graph. Now, that doesn't mean there aren't other things to do. There are things that can happen. Okay, first of all, this was where you just had a product of linear factors. Now, what do we mean by irreducible quadratic factor? some of this wasn't visible on the board. I've got to pay more attention to that. Most of this was visible. What I wrote over here at the left didn't quite make it. Okay. But you heard me say it all, and there's not really that much here. Just it approaches plus infinity as x approaches negative infinity. It's obvious anyway. Okay, now I just wrote an irreducible quadratic factor can't equal zero, so it can't be factored. Okay, and that's actually the definition of an irreducible quadratic factor. Okay. X squared plus 5x, uh-oh, yeah, that's all right, plus 12 can't equal zero. That's right here, the discriminant is b squared minus 4ac equals 25 minus 48 equals negative 23. So if you try to set this equal to zero, you're going to get a negative 23 under your square root. Okay? So it can't equal zero. Can't equal zero for any real number, at least, because it's only equal to zero for these for a complex number. Okay? So you kind of want to store that away. That's what we mean by irreducible. So product let's take a polynomial kind of similar to this one, with some of the same factors. Okay, so I've just picked out the 2x minus 7 and 2x plus 5, x squared plus 5x plus 12. Okay. P of x equals 0. That's where we're going to start. Let's start find out what P of x equals 0. Well, that breaks down into 2x minus 7 equals 0. 2x plus 5 equals 0. X squared plus 5x plus 12 equals 0. And that would be perfectly okay. You don't have to figure out whether this is irreducible because you're going to figure it out when you set it equal to 0. Okay, so x equals 3.5, x equals negative 2.5, x equals negative 5 plus or minus the square root of 5 squared minus 4 times 1 times 12 over 2 equals negative 5 plus or minus the square root of negative 23 over 2. And that's not a real number. I just write down not real. Okay. So what we can do we can say that we have two x-intercepts. At x equals 3.5, and at x equals negative 2.5. So we're going to be able to mark 2 points on our x-axis. And we could find the y-intercept. If we evaluate our polynomial at 0, we're going to get negative 7 times 5 times 12, which is negative 420. So our y-intercept is at negative 420. The thing is still going to have an x to the fourth. If we multiply 2x by 2x, we get 4x squared. Multiply that by x squared, we get 4x to the fourth. Okay? So this thing's going to act like 4x to the fourth if we zoom back, just kind of like this one did. Means it's still going to go way up on both ends. That makes sense? So I'm not going to do that because I don't have a lot of room here. But I can say, okay, well, by the same reason I used down here, I'm going to do this. It's going to do this. The long run behavior, it's going to go to infinity as you go to the right. It's going to go to infinity as you go to the left. So this is a pretty easy graph to draw. You just draw it down here, kind of flatten it out pretty good here, and then bring it on back up. That'd be all there was to that. Okay. So let me ask you to do an example, a couple examples. Try to figure out how to situate the board so you can see a lot of this. This is far to the right as I think I can manage. Gives me this much space over here so I can write down a couple of polynomials. This one's a little easier, but you can apply the same principles. Okay. So once you do this one, and then Okay, I've got four factors on this one. I didn't have room to write them all out and keep this board visible. But just go ahead and start with the first one and see how much of that you can do. Okay, now, some people read that plus as a minus. Some people read that minus as a plus. Okay, so everybody got a different graph. That's okay. I'm going to do this one. Um, okay, again, the zero property multiplication says the only way this can be zero is if one of these is zero, and there are three ways that can happen. One if x equals 3, everybody got the zeros, or x equals -5, or x equals 7. Okay, y-intercept, p of 0 equals 0 minus 3 times 0 plus 5 times 0 minus 7 equals -105 in this case. So we already know a good bit about the graph. It's 0 when x equals -5. It's 0 when x equals 3. And it's 0 when x equals 7. The y-intercept occurs when x is 0, y is -105. Well, I can put y equals -105 wherever I want to, as long as it's below the x-axis, I'm going to put it there. And the reason I put it there is I don't have another place to put it because of all the stuff I got below it. Okay, that's all right. So now that gives me 3 points on the x-axis and a point on the y-axis. And everybody got 2 points on the x and the y-axis. Okay, and everybody made plausible attempt at drawing the graph. But you got to know what the long run behavior is. So long run, mean term, the highest power term is x cubed. Because you're going to have an x from here, an x from here, and an x from here. Okay, the graph of x cubed it's a cubing graph where we've zoomed back on this graph. Now, the way I usually say this is the graph is basically an x cubed graph with some wiggles in the middle. Okay, some wiggles near the y-axis. And the wiggles are going to make it do this. But the long run is here and here. So I can say, okay, this graph has to go down this way has to go up fast this way. Just got to go through these points. Okay, so you got to start below this one. Is there no more zeros to the left? Uh-oh. I did a bonehead thing. Your y-intercept is at plus 105. -3, -7, +5. I've got two negatives. It's at y equals, it's at 105. And the reason I realized something was wrong was I can't come up through here and then get to this point without going through the x-axis. And the only way I can go through the x-axis is with a number that makes this 0, and the only numbers that make it 0 are -5, 3, and 7. Put any other number in for x, and none of these is 0. You multiply three numbers that aren't 0, you're not going to get 0. So quick modification here. We'll get rid of most of that line. Get rid of that point. Now we see, we come up from down here, go on up. We probably go a little past there. Then we come back up. Now you can see that this graph is going to continue on and look like this. And these little wiggles are just, within a short distance. Yeah, if you zoom back, these things are just going to be in a little part of the graph near the y-axis. Okay. There you have it. Now I think we're out of time. So we're not going to get to do this one. But Open Math will fill in the blanks and some other things we weren't able to talk about. We'll talk about it a little bit next time. Okay.